let's do some basic thermodynamics. Thermodynamics, remember, is the study of temperature that's changing. So let's look at the work done by a gas. Suppose I have a piston, and we're always dealing with pistons, and I put in a certain amount of gas. As I add heat, as I raise the temperature, the volume of the gas is going to expand. As the temperature rises, the volume goes up, and the gas exerts a force on the piston. The piston is this round stopper. So the work done is equal to force times distance, and that force is delta y. But remember, pressure is force per unit area, so the work done is pressure times A delta y, but A delta y is this change in volume. So the gas does work that is equal to the pressure times the change in volume of the gas. Now, the work done is always going to be the area under a PV graph. We do a lot of PV graphs in this class. So the work done is the area, which is H times B. Now, we always have work as minus P delta V. This negative sign is very confusing. Since work is done by the gas, work done by the gas is going to have a positive volume. We have to understand that the gas itself is using energy. So it's losing energy, so you get this negative sign. So basically, if delta V is positive, this is work done by the gas. If delta V is negative, this is work done on the gas. So work done by the gas is going to be negative. Work done on the gas is positive. And now let's talk about internal energy and heat. All of the energy inside a system is called its internal energy. And we're going to use delta U to designate that it is internal energy. When you add heat, you're adding energy. This causes the internal energy to increase. Imagine you're putting hot water into a bathtub. The internal energy of the bathtub increases. Now, both heat and energy are measured in joules. And there's usually an increase in temperature when you have an increase in internal energy. If the change in temperature is 0, then we know that the change in internal energy is 0. Now, the internal energy of a system tends to increase when heat is added and work is done on. Think about it. You're rubbing your arm. Work is being done on your arm. Your internal energy increases. So, we can write this in two ways. The change in internal energy is the heat added plus work done on the system. Or the internal energy is heat added minus work done by. You can combine this into one equation. Delta U is the Q added minus the heat done by. Okay. Remember, delta U suggests a change, and the delta here, this Q added minus Q by, you're really adding a negative. Let's do a problem. Sketch a PV diagram and find the work done by the gas during the following stages. I have a gas expanded from a volume of 1 liter, so I'm going to come over here to 1 liter, 1 liter to 3 liters at a constant pressure of 3 atmosphere. So this is what my diagram looks like. It starts at 1 liter, goes to 3 liters. Now, the work done by is P delta V, so it's 3 atmospheres, and I'm going to convert that to pascals. 3 times 10 to the 5th pascals. Final minus initial gives me a work done by the gas of 600 joules. the gas is then cooled at a constant volume until the pressure falls to 2 atmospheres. So this is the case right here, it falls. But we can see the work done is 0 because the change in volume is 0. Now the gas is going to be compressed from 2 atmospheres, from 3 back down to 1. So this is what the diagram would look like from 3 to 1 at 2 atmospheres. The work done on is minus P delta V. So now the pressure is 2, and it starts at, final is 0.001, and its initial is 0.003. So I get the work done on is negative 400 joules. The gas is now going to be heated until its pressure increases from 2 atmospheres to 3 at a constant volume. When the volume is constant, the work done is 0 because that change in volume is 0. So what's the net work? Now, as a rule of thumb, if the system work is going clockwise, the net work is going to be positive. If it's going counterclockwise, then the work is going to be negative. Because the net work is the area inside this shape. So 600 minus 400 is 200 joules. Now let's work this example. These sorts of examples are just what you can expect during a legitimate AP problem. Suppose we have a series of thermodynamic processes are shown. In A to B, I have 500 joules of heat added. So that's from here to here. In the process B to D, I'm going to have 600 joules of heat added. Let's fill in the chart. Well, let's see. From A to B, I know I have 150 joules of heat added. It was given to me. From B to D, I'm going to have 600 joules added. So to find the heat added from A to B to D, I simply add those two numbers and I get 750 joules. Now let's find the work. From A to B, there is no volume change, so I have 0 work done. From B to D, the work is going to be P, or 8 times 10 to the 5th pascals, times delta V, or 5 minus 2, or 3 times 10 to the 3rd meters cubed. So I get a work done is 240 joules. So from A to B to D, I add those two, and I get the work done is 200 joules. Now let's find the change in internal energy. For A to B, the change in internal energy is Q plus W, or 150 joules. From B to D, it's 840 joules. And the total change in internal energy from A to B to D is 990 joules. Could have added here or here. Now, let's look from, we're going to go from A to C to D. So we're going to reverse this process. The total energy has to be 990 joules. Let's look at the work done from A to C. From A to C, we have a pressure of 3 times 10 to the 4th pascals and a delta V of 3 meters cubed. From C to D, we have 0 work done because the volume does not change. So, from A to C to D, we have a work of 90 joules. Now this leaves a heat of 900 joules being added from A to C to D. Now let's talk about a variety of thermodynamic processes. You need to know the difference in these. Isothermal means same temperature. So an isothermal temperature means the temperature at 1 is going to equal the temperature at 2. So as I expand this gas, the volume increases so that the temperatures don't change. But you remember, when the temperatures don't change, the change in internal energy is 0. Now, the change in volume is positive. So, the delta U is Q minus the work done by. So I get, a Q of, let me back that up. I get a Q equal to the work done by, excuse me, is equal to, well, that's not working. Let's just stop this.